start. Can you hear me and can you see the slides?
Yes.
Wonderful, thank you. So welcome to today's lecture on chromatographic separation processes. As I wrote in the email, I would like to focus today on protein purification. We touched that topic already certain times during your presentations, but I think it would be a good idea to have an overview of all the methods available for protein purification on one glance, and also to see that often a combination of these methods is necessary to perform the goals, to reach the goals which are necessary. So in terms of purity and perhaps also of yield. So that's what we will go through the next hour. I will give a short introduction into the protein purification and into downstream processing, which has more steps than just the separation steps. And then, I would like to focus on the chromatographic methods for protein separation, and I will conclude with a short summary today. So let's start with this slide. This is an old photo from Baron Jöns Jakob Berzelius, who was a Swedish chemist. He was considered, together with others, to be one of the founders of the modern chemistry. And he also were thinking about proteins, and as the word itself is derived from the Greek word proteos, which means of the first rank. And this was given to this kind of substances in order to stress the importance of this group of organic compounds by Baron Berzelius. Okay, I think this is more or less what you know from school. What are proteins? And so we call them servant of life. Proteins are made from amino acids by condensation and elimination of water here. So depending on the number of amino acids which are polymerized, we talk about the dipeptides, tripeptides, oligopeptides, polypeptides, and also proteins. And proteins then usually contain more than 100 amino acids. Most enzymes are enzymes, but we also find proteins as regulatory or and structural substances here as well. Okay, not that long ago like Berzelius, but also 2 or 3 generations before, there was this guy, Albert Lehninger. There's also a book written by him, The Principles of Biochemistry. And he was thinking about how to separate proteins. And he said, and why? And he said, to study a protein in detail, the researchers must be able to separate it from other proteins and must have the techniques to determine its properties. That sounds easy, but so the problem is terrible, because given that cells contain thousands of different kinds of proteins, how can one single protein be purified? And so what can we do, or what needs to be taken into account? So the methods for separating proteins should take advantage of the properties that vary from one protein to the next. And what are these properties? So they include, for example, the size, the charge, and also binding properties. And we will see later that these properties are really used for specific separations. Okay, so once again, the reason for protein separations. So on one hand, we might be interested in the structure, the sequence, function, what is a regulatory effect of certain proteins, and in order to investigate, to be able to investigate these, we before need to purify a single protein. This is at smaller scale usually, but there are also large scale production processes of proteins for different applications. Some of them are listed here, so very yeah, typical application of proteins are, for example, in the medical area. Insulin is one example here, which is a peptide hormone, usually produced by beta cells of pancreas. And so formerly it was produced from slaughtered cattle waste, but today we have genetically engineered synthetic human insulin, since 1980, more or less. We find enzymes also in food processing, for example, in bakery. Xylases, amylases, and cellulases are used in fruit juice processing. Cellulases and proteases are used in washing powder. There are enzymes included, and for example, in pulp and paper industry, we use salinases for the bleaching of pulp. These are just a few examples, so there are many more areas of applications for proteins. So if we think about the scale of separation and what quantities are necessary for certain applications, so if we just want to do protein sequencing, for example, do identification by mass spectrometry, for example, we only need a few nanogram to microgram. If we want to do further functional or physical chemical studies, so we might need a few gram. Then if we already come to the commercial area, then if there are very specialized proteins, then also a few gram are necessary, usually only. But there are also proteins which are produced in much larger scale. So commercial enzymes or antibodies for in vitro diagnostic purposes, for example, here a few kilogram might be of interest, and here usually these are moderately or highly purified. If we have proteins for the in vivo therapeutic, like the diabetes, for example, then we have highly purified proteins and scale up to 100 kilogram. Then there are also bulk industrial enzymes, for example, for the washing powder. Here it's more than 1 ton, and usually they are less purified, so not non-purified, but not very high purified. And for example, the milk-derived proteins produced for bulk food applications, here we have more than 100 tons production per kilogram. 100 tons production per year. Okay, so what are usually the raw material for purification of proteins? So usually it's a fermentation broth, which contains a lot of water, and it also contains the proteins of interest, and usually the concentration of the raw material in the fermentation process is quite low. So you can see here the logarithmic scale. So this is a pure water, 100%, and ethanol we can have, for example, 10% in the fermentation process. Similar range is for the citric acid, but if we go to proteins, then you can see the concentration range in the raw material is much lower. And here, for example, this factor 8, which is an essential blood coagulation factor, it has a concentration of 10 to the power of -5 in the raw material. And yeah, so if we want to purify and concentrate these proteins, we need processes for that, and the more processes, the more expensive the final product will be. So in general, 50 to 70% of the total production cost in bioprocesses are generated by the product purification processes. It means if we can improve the product purification processes, these would promote the efficiency and the cost of the process, and in the end make bioprocesses more competitive to conventional chemical processes. Yeah, so I told you already, so usually we need several different steps, and even each step has, might include more than one step here. But yeah, usually we start with a sample preparation. Then from that we produce an extract and do first a clarification by, for example, filtration or centrifugation. We will have a desalting step here. We can have a buffer exchange, and perhaps we are able to separate, but to precipitate some proteins selectively, but that's only sometimes possible. Then we have another capture step. From that, we have an initial purification of the protein, which will be partially purified now and already enriched a bit. We will have an intermediate purification step, which will remove the bulk contaminants, and usually we come out after this step with a protein purity of 60 to 80%, and to come to higher purities, to more than 90%, we use a so-called polishing step, which is used to remove the trace contaminants as well. Okay, so the downstream processing, right now we can classify into primary unit operations and secondary unit operations. The primary unit operations are shown here. They are downstream, and downstream means after the fermentation process. So usually we have to start with a cell disruption, because usually the protein is inside the cells, and so we need to wrap the membrane of the cell by a certain technique. Yeah, we can do it, for example, by sonication, by pressure cells, or by enzymic lysis. After that, we will remove the solid parts of the cell, for example, by centrifugation and filtration. And after that, we will do a dewatering step, which means we will remove at least some of this high amount of water to have a first concentration step here, and to reduce the volume, we have to carry along the process. Yeah, this can be done, for example, by ultrafiltration. It is also possible by precipitation of the proteins, by spray drying, for example, or by dialysis. Let's think about this precipitation here. What is this? So usually the proteins or the solubility of proteins depends on, among other things, the salt concentration in the solution. Yeah, it also depends on solvent additives, pH, and temperature, for example. But let's focus on the salt concentration, which correspond to the ionic strength. And the effect is that the solubility of a protein at low ionic strength generally increases with increasing salt concentration. And this is because the salt stabilizes the charged groups on the protein molecules and thus attracting the protein into the solution. Now, this part of this mechanism is called salting in. This comes to a maximum, and after that, at high ionic strength, if we further add salt, the solubility of the proteins will decrease. And this is because the salt concentration bind the water, and this is no longer available for the hydration of the proteins. And thus the proteins will aggregate or precipitate according to their hydrophobicity. So this is so-called salting out. So this effect you can also see here on this figure a bit. So again, the solubility increases as the ionic strength increases, because more and more of the well-hydrated anorganic ions, this blue circles here, are bound to the protein surface, and that preventing the aggregation of the molecules. So this is the optimum here then. This is the salting in, so this is the solubility is increasing here. And at very high ionic strength, the salt withdraws the hydrate water from the proteins, and thus leads to aggregation and precipitation here. And this is the salting out. And yeah, and we can use this to precipitate them, and then yeah, for example, do some filtering and remove water, and by that concentrate the solution in a first step. Okay, so the secondary unit operations are also several different ones. So first of all, there's a protein purification, which is usually chromatography, different chromatographic separation processes. And yeah, if we have finished the purification and come up with a high purified protein, then we need perhaps some immobilization, or at least some stabilization. We need beading or prilling in order to be to have a product which can be given to the customers. So, and at least yeah, we need some packaging here, sterilization perhaps, bottling, and others. So these are the secondary operations. Okay, so as Lening already said, so we have to look for the different protein characteristics. If there are the stability, for example, solubility, the mass and shape of the proteins, what about the surface charge, what about surface hydrophobicity, and there might be some specific binding characteristics. yeah, regarding the stability, this cannot be used for separation, of course, but we always have to take care about it. So we have to perhaps avoid high temperatures or high acid concentration and so on. So there might be several different factors we have to take care about in order to have a stable protein solution. Oxidation might be a problem. However, these other characteristics we can use for as mechanisms in separation methods. So, for example, the solubility can be used for the selective precipitation of proteins, for example. Different mass and shape can be used in size exclusion chromatography. The different charge of the proteins can be used by ion exchange chromatography. The hydrophobicity, as the name already said, can be used in hydrophobic interaction chromatography. The specific bindings is used in affinity chromatography. So I will explain these different chromatographic methods in more detail in the next half an hour. Yeah, so this is the overview. And yeah, we already discussed it on the last slide a bit. So let's start with the size exclusion chromatography. The size exclusion chromatography is also known as MJ filtration chromatography. The difference here is that if we talk about filtration chromatography, it's only an aqueous mobile phase, while size exclusion chromatography is a more general expression. This can also here also organic solvents can be used as mobile phases. Yeah, so size exclusion chromatography will separate or will enable the separation of molecules on the basis of their molecular size. Shape plays also a role, but yeah, usually it's more size. And what is important that to be able to separate two different proteins, we need at least a difference of 10% in molecular mass. The stationary phase in size exclusion chromatography is a porous matrix. The pores are of different sizes, and these sizes of pores will determine the fractionation range a matrix is offering. So, but in general, always the large molecules will include first because they can't enter into any of the pores. And the small molecules will penetrate into the different pores, and the smaller into the more pores they can penetrate, and that means their path length will be longer, and so the dilution time is longer. Yeah, so the size exclusion chromatography can also be used to determine the molecular weight of an unknown protein, for example. And this matrix is really just a porous gel, for example, and which is not functionalized with any active groups, for example. And unlike ion exchange chromatography or hydrophobic interaction chromatography and so on, the protein here is not absorbed onto the resin, so it's more a sieving effect here. So the basis is not so it's not no absorption chromatography. Yeah, so this is a scanning electron micrograph of an agarose scale, just to get an idea on how it looks like. You can see it's a highly porous material, and you can imagine that the molecules will have longer and shorter ways going through this material. So here are some commercially available filtration materials. Yeah, you can see they're available in different bead sizes here, in the range from 10 to 150 micrometer in bead size, and they offer different fractionation ranges. This is given in Dalton here. For example, this Zefatec G75 offer a fractionation range from 3,000 to 80,000 Dalton, or for example, the Superrose 6 here, it offers a fractionation range from 5,000 to 5 million Dalton. You can see you have to decide, you have to find a proper resin in order to separate your proteins of interest. It means you already need an idea on what is the molecular weight of the target protein in order to choose a proper resin here. So this is how a typical size extrusion chromatogram looks like. So all the peaks elute within one column volume, because there is no adsorption. And yeah, so usually we after some equilibration where perhaps some impurities are diluted, the sample injection takes place, and then right after everything with a very high molecular weight will elute, and yeah, so this is a mixture of different components which are not further separated from each other, but they have all a very high molecular weight. Then there is a certain retention time, elution volume here, where we can separate components. This is the fractionation range here. These are the components with intermediate molecular weight. Here we can come to a high purifications here, high concentration. And at the end of this chromatogram, we have a peak with molecules with low molecular weight. Also here, this is a sum of different components, which all have a low molecular weight. So if we look closer to this kind of chromatogram, we find the typical parameters we also find in, as we know from other chromatographic processes, but in size exclusion chromatography, it's usually described by the volume and not by retention time. So we have the retention or elution volume of the protein, which is the volume at which the particular protein elutes. As we can transfer the retention volume to the retention time by dividing the time by the flow rate, the column flow rate. And then, so we have this last peak here, these very small components. These give the VT, the total mobile phase volume in the column. This can be estimated from a very small dye, for example, like riboflavin. And here this peak with all the very large components is given by the interparticle volume of the column, and this can be estimated from a big molecule which cannot enter the pores at all. So, for example, the blue dextran is used for that. The different resins are described by two numbers. One is the fractionation rate, I showed on the table already, which is the size range over which the column can resolve the proteins. And the exclusion limit is the size of the largest protein that can enter the pores, and all proteins larger than that will elute here at the B0. So if we know the retention volumes and the interparticle volume and the total mobile phase volume, we can calculate the distribution constants. K average here, K here is always between 0 and 1. You can see here, and with increasing molecular weight, the distribution constant becomes smaller. So this can be used for the determination. Yeah, is there a question? Okay, so this can be used for the determination of molecular weight. So what needs to be done in order to determine the molecular weight here? So first we need to calibrate our system. For that, we will inject a mixture of known proteins and run it through the column. The mixture can, for example, be this one. We need something with a very small size, and very small one, and a very large one. So the large one here is the blue dextran, which gives us a B0. The VT here, for example, is given by riboflavin, for example. And so after that we can calculate the distribution constant for each of these proteins by this equation shown before, and then we can plot these distribution constants as a function of molecular weight in a logarithmic scale, and this gives a graph like that. And now we can inject the protein of unknown molecular weight and elute it in the same way, and then we calculate the K average of our unknown protein, perhaps it's here, for example, and then we can calculate the molecular weight of this unknown protein from the standard curve. That's a very simple method. Okay, so in general, the advantages of size exclusion chromatography is that it's very simple and predictable. Unfortunately, it has a low capacity, and the load must be non-viscous. So so the concentration are not allowed to be too high here. So, but it's good for a 2-fold to 6-fold purification. Another method which is available is the ion exchange chromatography. This is based on different charge-charge interactions, which are according to the ion exchange affinities of the sample components. This now is an absorptive technique. The solid matrix, here the gray one, is either positively charged, then it's an anion exchanger, or negatively charged, then it's a cation exchanger. So this figure here on the right, it's cation exchanger. So the matrix is negative, it attracts the positive cations, and therefore it's a cation exchanger. And yeah, there is a competition of the sample ions with the salt ions in the mobile phase, which can also be used as an elution strategy. So we can use for elution a higher salt concentration, or we can also use a different pH, which might change the charges of the proteins. Yeah, in ion exchange chromatography, we have active sites fixed on an organic resin. So this resin can be, for example, polystyrene divinylbenzene. In anion exchange, we need positively charged groups, like, for example, the quaternary ammonium groups. In cation exchange, we need negatively charged groups here, like the sulfonic acid or the carbonic acid groups. And yeah, the separation is influenced by choosing a proper ion exchanger, by the pH value, the ionic strength, and the counter ion of the mobile phase. Yeah, let's say a few words about the protein net charge, the pi and pH. So I'm sure you know that all proteins have ionic group on their surface, and these groups are charged or neutral depending on pH. We do have this acid group here, or the amino group, and the net charge on a protein can change or will change with different pHs. So it depends on which side of this equation the glycol is. There is a certain pH where the net charge of a protein is 0, and this is called pi. It's an isoelectric. And yeah, and to have a closer look or to think about the application in ion exchange chromatography, then, so at pH which is higher than the pi, the protein net charge is negative. So we would use an anion exchanger at a pH smaller than the pi, the protein net charge is positive. In this case, we would use a cation exchanger, and at pH is the same as the pi, the protein net charge is 0. It means there won't be any binding to a charged surface in ion chromatography, ion exchange chromatography. Yeah, so we can influence the net charge on a protein by pH. This is shown here. So at a pH higher than the target pi, I told you we would use an anion exchanger. Then we are here in this range. If the pH is smaller than the pi, we would use a cation exchange resin, which is in this case here. And yeah, and what would we choose? So we have to look for a pH where our target protein is stable. And by that we can choose a suitable pH, and by that also suitable metrics for the separation. Yeah, so isoelectric point of proteins differ. So here you can see from acidic ice up to alkaline PIs, everything is possible. So this is how an ion exchange chromatogram looks like. This is again shown as not in retention time, but in retention volume here. So we need at least 2 column volumes to equilibrate the system. Then we would inject the sample, and then the elution starts, and it starts with eluting everything which is unbound, and then there's a certain time where we can separate the components, proteins, and finally at the end we need to change the properties, for example, by having very high salt concentrations, so that everything what was bound to the matrix will be washed out. And then we need some re-equilibration before we can again apply or inject the sample. The red line here in this graph shows the salt concentration in the mobile phase. During our presentations, we were sometimes talking about the gradients. This is kind of gradient, so it means that we change the salt concentration in the mobile phase. Here it starts from a very low concentration, then we have a linear gradient with increasing salt concentration, and then we have this is a stepwise gradient to very high salt concentration, and then we have another step gradient here to go to low salt concentration again. So this is a linear gradient. We could also do a step gradient here in this area, but usually it's run like that. And of course we also need the re-equilibration time to remove or to come back to the low salt concentration in order to enable the binding of these proteins here. So if we would go on with a very high salt concentration for the next injection, of course everything will elute directly. Okay, so the advantages of ion exchange chromatography are that we can use very large sample volumes, also not only volume but also the amounts of protein can be high, that the packings are very robust, and there is a huge number of different combinations of mobile phases and stationary phases, so that the conditions are quite flexible. We saw from the chromatogram there are also some disadvantages. For example, that the protein has to be at the same pH and salt concentration as the column, so that sometimes we need an extra buffer exchange step. And for very large volumes, for example, it's a bit inconvenient. So for example, the post-chromatographic high salt concentration, which needs to be removed then, for example, by a dialysis, desalting, or dilution step. So we will have an additional step here. Okay, so the third of these 4 very important separation methods for proteins is the hydrophobic interaction chromatography. This is based on this separation is based on the surface hydrophobicity of the molecules. And what is the hydrophobicity? So we have on the surface of each protein there are hydrophobic side chains. Most of them are buried inside the proteins, but some are also on the surface. And so here on this figure here, you can see an example. For example, we are looking for the most for the dark red ones with the most hydrophobic areas. So these, if we can have an interaction of these areas with a matrix, for example, this could enable the separation, and perhaps also less hydrophobic will be included in interactions. So this hydrophobic interaction chromatography then separates molecules according to the surface hydrophobicity. It's an adsorptive technique. We have an adsorption at high salt concentration. We will also here apply a gradient or a step illusion, and this is a complementary method to ion exchange or side electron chromatography. There was or there is a question in the chat I just saw, so it's regarding the ion exchange chromatography, and it's a question about scaling and fouling issues. And yes, of course, always if we deal with fermentation broths, we also have a problem of fouling, and at high salt concentration, perhaps also scaling. So scaling is easy to avoid. We can regularly wash with water solution. Fouling, for fouling, we need harsher washing steps. So it always depends. So we can include a regular washing procedure after a certain time in order to enable the longer usage of the matrix, or we have to change matrix once in a while. So at least it's quite important to take care about it. It means that you always have to check if your conditions are constant. So, or if your efficiency is decreasing, and then latest at that point, you should wash, do an extra washing step, for example, cleaning step, or change the material. Okay. You're welcome. Okay, so coming back to the hydrophobic interaction chromatography, the principle is a bit like the salting in, salting out, what we saw at the beginning today. However, the stationary phase is a non-polar matrix. So we have the octyl, phenyl, or butyl, which we know from reversed phase chromatography. But in reverse phase chromatography, these groups are attached to silica usually, and in hydrophobic interaction chromatography, these groups are attached to an inert matrix like cross-linked dextran, cellulose, or rubose. So the typical material which is used in protein for protein separations. And yeah, so what we do, we load the column at high ionic strength, so with a high salt concentration in the buffer, so the water of the hydration is removed from the proteins, and those with fewer polar residues on the surface will lose their water easiest, and their exposed hydrophobic regions will then bind to similar groups on the resin. And for the elution strategies, we can again we can decrease the salt concentrations. This will augment hydrophobic interactions, or no longer. This will decrease the hydrophobic interaction, and or we can increase the concentration of a detergent, so numbers are wrong here, and could also do some changes in pH. This would also can also lead to the ionic repulsion, for example. How does a chromatogram in hydrophobic interaction looks like? Here we start, as I just said, with very high salt concentration. And yeah, we need some equilibration of the column, then we would inject. And then, as it's usually the case, first everything unbound will elute, and then we will start the gradient with decreasing the salt concentration in the mobile phase, and by that we could fractionate, separate and fractionate some components, and at the end, at salt-free concentration, we will be able to elute everything which was tightly bound to the resin. And before we could inject for the next time, we need to re-equilibrate. In this case, we need to come back to the very high salt level, and then we could do the next injection. And also here, as we just discussed for the ion exchange chromatography, also here, this is if we deal with protein solutions, fermentation broth, and so on, we also have to take care about fouling issues, so that re-equilibration can also be that we could also add some additional washing steps here with other solvents, which might help to remove the material which is left on the column. Okay, so the advantages of hydrophobic chromatography. So here we can also use large sample volumes and also large concentrations. Here the packings are robust as well. Also here we have a huge number of variations which offer flexible conditions. The equilibration here is easy. We could use this type of chromatography straight after the precipitation with the ammonium sulfate, sorting out here, because at that point we already have a very high concentration of ammonium sulfate in our solution. The gradients are stable, but disadvantage is that sometimes the high salt concentration which are necessary for the binding cause precipitation, which might be which is a wanted effect on one hand, but of course in chromatography we don't want to have precipitation of proteins in the column, so this need to be avoided. Okay, so and the last of these big four chromatographic methods for protein separation is the affinity chromatography, which is based on the unique biological specificity of the sample ligand interaction, which is a very powerful method for purification. The stationary phase is in inert matrix with a covalently bound ligand, which is chosen in a proper way to interact with the target protein. And so only this one kind of molecule will be attracted to this ligand and attached to it, and all the others flow through. That we will have a very high specifically here. So what can these ligands be, for example? So here there are several different available. So for example, here if we go to biospecific affinity chromatography, we need an affinity ligand here, which will bound to the enzyme and build an active site bound enzyme here then. Or if we look for immunoaffinity chromatography, our ligand will be an antibody which interacts with the protein epitope and build an antibody-bound enzyme here in this case. So yeah, here in this table you can see different combinations which could be used for the specific binding of proteins. For example, protein dye is a very useful, often used method. The plasminogen lysine complex, for example, histidine nickel is also a possibility, and sometimes also if these parts of the molecules, these monomers, are not included in the protein, or at least not on the surface, then we could also add some tags. So we let our protein react so that we have a certain tag for the protein, and then we have specific separation, and after we could remove the tag again. But this will need some additional steps here. Yeah, so I already mentioned most of them. So there are several different affinity chromatographic methods available. Yeah, so this is a scheme for it. So we have a sample which fits into the ligand here, and the problem then is how to elute it, because it's a very strong interaction here. So what we can do is we can increase the concentration of free ligands, for example. We could add a reagent which competes with bindings, something here with a stronger affinity, for example, or we could change the pH, which will influence the surface charge here of the protein, and then also there is no longer this interaction here. And this is just, we add some excessive ions here, which block the charged groups on the ligand. Chromatogram then looks like that. So we also start with an equilibration before we inject our mixture. Then everything is first eluted, which is not interacting with the stationary phase. So we wash away everything which is unbound, and then we have to change the elution buffer to change the interaction here, and then our target protein will elute as a relatively short here. And after that, we need also here a regeneration. Okay, so one example for that is the human plasma, or the plasminogen separation from human plasma, which is only 0.3% of the total protein. And the total protein is 70 milligram. And yeah, we saw that the plasminogen has a high affinity to lysine. So we can build a column with lysine as a ligand on agarose, for example. And we can load the protein mixture, wash, and do the elution with a lysine analog. And as a result, then in one step we have a purity of this plasminogen of higher than 99%, and the yield is also very high with 90%, more than 90%. Okay, so the advantages of affinity chromatography: it offers a high affinity with binding in the micromole, nanomole, or even the picomole range. It binds all or none, so we have an excellent recovery here. And also here several variations are possible, especially if we use tags. Unfortunately, this is not always the perfect choice or the only choice, because sometimes we have a spherical hindrance which lowers the capacity. To remove the material, the target proteins from the matrix, sometimes we need very harsh dilution conditions, and the application is also limited by the selection of available affinity chromatography. So it's not, yeah, it's a quite selective method, but not the only, and not the solution for everything. Okay, so one last example to show that we need more than one purification step to get a certain purity out of for something. So this is a purification of a monoclonal antibody here. We start with a fermentation broth, a volume of 10 liter, which contains 0.6 milligram per milliliter of the target protein. So as a first step, we would do a hydrophobic interaction chromatography, which needs 3 hours. It will be on a small column, 10 centimeter in height and 10 centimeter in diameter. We come out with a fraction of 1.4 liter. This needs, with this we do an ion exchange step. After that we have a fraction of 0.4 liter. This we need to dilute by a factor of 10 and in order to adjust pH, for example. And yeah, so then we can do the size exclusion chromatography as a last step, and our final product is 0.7 liter, and in this we have a product of 3 point, and then we remove the water, and then we will have a product of 3.7 gram, and the purity is 99%. And the overall yield is 61%. So it means during the steps, of course, we will always lose a bit of our target protein, so that overall yield is a bit lower than here. Okay, so to give a summary of the methods, so these are called the big four of protein separations, chromatographic separation methods. So we have the size exclusion chromatography, the ion exchange chromatography, the hydrophobic interaction chromatography, and the affinity chromatography. And we were discussing about their capacity. The size exclusion chromatography has a low capacity. All the others have a high capacity. If we look for the cost for it, then the size exclusion and the ion exchange are relatively cheap methods. The hydrophobic interaction and the affinity are a bit more expensive. And if we look for their position in their recommended position in the purification scheme, then it's good to start with the hydrophobic interaction chromatography right after the precipitation step, and yeah, the ion exchange and the affinity can be done at every position, and the size exclusion chromatography, as the capacity is low, should be done late in the purification scheme. Okay, so to conclude, there are different chromatographic methods available. This big four: size exclusion chromatography, ion exchange chromatography, hydrophobic interaction chromatography, and affinity chromatography. The equipment for biochromatography is also available commercially, and also at large scale, production scale. You might remember I showed these glass and acrylic columns also on very large scale, which can be used for biochromatography. We know that high purities of products are only possible by a combination of different chromatographic methods. This leads to lower yields, and of course, the more methods are used, the more method development is necessary as well. So the method development for purification of protein is usually a bit more extensive. Okay, that's my last slide today. Are there questions left? Okay. Yeah, if this is not the case, then I thank you for being here today. And yeah, I will stay again for a couple of minutes here if there are some questions you want to ask me. And if not, we will see us next Friday in the morning, 9:45, and we will have online again. And we will have the last presentation. I think it's 2 or 3, and then we will have another lecture on my side, and I think probably I will talk about chiral separations. There's one question in the chat. If you don't know too much about your protein, which method is the easiest to start with? Okay, so perhaps if you don't know too much about it, so I mean, what does that mean? If you even don't know the size, then it might be good to start with a size exclusion chromatography to determine at least the size. So I mean, if you don't know, so we can make a difference of protein separation for analysis or for production. If we want to produce really in large scale, then of course we already know a lot of our protein. And okay. And if we have for analytical purposes, yeah, then perhaps you would start with a size exclusion chromatography and to learn a bit more about it, and then perhaps next an ion exchange chromatography. And yeah, I think this would be the 2 methods to start with: ion exchange chromatography, size exclusion chromatography, to get more idea on what are the properties. Any other questions? Okay, so that's not the case. Then, yeah, thank you again. See you next week. And I will be here for a couple more minutes. Thank you. Bye-bye.
Bye-bye.
Thank you. Goodbye.
Thank you.
Thank you.